So, good morning, good afternoon, good evening to all of you. And I'm really very happy to see uh, old friends, but also young ones. And so I wanted to tell you about the century of adiabatic evolution. As I, I don't think I'll teach you anything, but perhaps I'll entertain you. Good, so this is the outline of the talk. I would like to start by history and telling some stories that go 100 years back, and then review a collection of results on the adiabatic, on various adiabatic theorems that exist. And then I would like to describe an idea that goes back to Cato and has been rediscovered by many people since then, independently, but after that. And this is the notion of spectral evolution. And I would like to discuss how the notion of spectral evolution is related to adiabatic theorem. And then I'll show lots of pictures, discuss a little bit why should you care about adiabatic evolutions? I hear an echo. And I think this will be mostly, until this part, this will be mostly simple things and entertaining, hopefully. I hope I won't annoy you. And then I'll get into slightly more technical things. So first I'll describe how one can describe the smooth part of adiabatic evolution. And at the end, I'd like to conclude by discussing the oscillations, which is the hard part in the adiabatic theorem. I don't know about your universities, but I think at the Technion, at least when I taught quantum mechanics, I never taught the adiabatic theorem. For undergraduate, this is considered, I think, a little too tedious. There are too much calculations. There is nothing you can summarize in 2 lines. So we don't teach this, I think, for undergraduates. And when you get into the graduate school, then everybody believes that the student already heard about the adiabatic theorem and nobody bothers to teach them the proof of the adiabatic theorem. And in fact, the proofs of the adiabatic theorem are a little, involved, too lengthy, too long. You can't summarize them in 2 lines. So even though the subject is 100 years old, you can still find papers now in the last 10 years where in an appendix people go into the trouble of proving the adiabatic theorem, even for matrices. Even for matrices, the proof is not completely trivial. So let me start. So I'll start by telling you stories. And I want to start with Paul Ehrenfest. In the days before quantum mechanics, before Schrödinger and Heisenberg wrote quantum mechanics as we know it, so quantum mechanics was encapsulated in this Bohr-Sommerfeld formula, which says that the PdQ for integrable system, the integral PdQ is an integer multiple of Planck constant. And this gave a classical mechanic meaning to quantum numbers. So the quantum numbers are integers. And it was a realization of Paul Ehrenfest that one way to think about about the action in the action angle variables as adiabatic invariants. And for example, in the case, if you take the harmonic oscillator, then the notion of adiabaticity is encoded in the fact that if the frequency omega dot is much smaller than omega square, this is a comparison that tells you that the period changes slowly, then the thing which is conserved is E divided by omega. So in the time-independent case, it is the energy which is conserved, but in the slowly time-dependent case, it's the ratio of E to omega. And so this is an example of an adiabatic invariant. And Ehrenfest wanted to make this connection between invariants and quantum numbers. I think Ehrenfest was not very happy about the new quantum mechanics, because somehow the new quantum mechanics, how would you say, superseded or made this nice observation of Paul Ehrenfest obsolete. And Paul Ehrenfest was actually, he was afflicted by depressions. And as you can see, he didn't live very long at the age of 53. It's a sad story. He had a sick child and he committed suicide and killed his child. So that's a sad story about Paul Ehrenfest. This is a remark which has very little to do with adiabatic invariance, but I discovered it recently, so I thought perhaps you would be amused as well. I think the most famous example of this adiabatic invariant for the harmonic oscillator is if the Einstein formula for counting the number of photons. So E divided by h bar omega counts for us the number of photons. And this is a formula that goes before the time of, it's earlier than Paul Ehrenfest's observation. And of course, it was suggested in Albert Einstein annum mirabilis in 1905. Now, in his paper, Einstein doesn't make any connection between the photon number and adiabatic invariant. But in his other famous paper, the one where he discusses special relativity, how Maxwell equation can be understood in terms of Lorentz transformation and Lorentz transformation of the electromagnetic field, Einstein makes a wonderful observation. And the observation is that E divided by omega is a Lorentz invariant. It's not an adiabatic invariant, but it's a Lorentz invariant. He considered the following amusing setup. So consider light with frequency omega hitting I would call it a detector or a screen. And you want to consider the energy absorbed by the screen. And you now want to consider this problem from two different frames. One of an observer where the screen is stationary, and one observer of a moving observer. So the two observers see different frequencies, of course, because of Doppler. And they also see different energies because the standard formula in Maxwell formula for the energy, you have to take account how the electric and magnetic field transform under Lorentz transformation. And then Einstein writes the following thing, that the ratio of energy is given by this root on the right. And then he makes the nice observation that the energy and the frequency both undergo the same transformation, which actually implies that the ratio E over omega is a Lorentz invariant. I don't think this this somehow led Einstein into his formula, but I thought it's an amusing observation. So since I won't teach you anything about the adiabatic theorems, at least I'll tell you a amusing anecdote. Okay, now if you look at books, or if you look at articles that try to give the earliest credit for the adiabatic theorem, you typically find that people give credit to the paper of Born and Fogg from 1928 as the first paper that proves the adiabatic theorem. And as you can see, here is beweist des adiabaten Satzes. So actually, this reference is inaccurate. It was actually Max Born who first proved the adiabatic theorem for matrices. So finite dimensional matrices with where the instantaneous energy levels don't cross. And he gave the proof in 1926. Now, the paper that people normally quote for the adiabatic theorem is the paper of Born and Fock from 1928, which extends the result of Born from 1926 to the case where you allow the instantaneous eigenvalues to cross. And Born and Fock showed that also in this case there is an adiabatic theorem. It says something slightly different. So in the case of a gap, an adiabatic theorem would say that if you start at the, say, the lower eigenvalue, you will follow the lower eigenvalue. But in the case of crossing, what you would do, you would follow the curves continuously. You would, in this case, you would still stay eventually at the lower eigenvalue. Now, so this is the result of Born and Fock. And it's actually an interesting result, which I think is not appreciated by many people because of the following, I don't know if I should call it misunderstanding or folk wisdom. So a gap in the system dictates the internal time scale of the system. So 1 over G is actually the internal time scale. For example, if you take the harmonic oscillator, the gap is omega, and 1 over omega is the frequency of the oscillator. So many people think that if G vanishes, this means that the system has modes which are arbitrarily slow. And if the system has modes which are arbitrarily slow, there is no notion of adiabaticity because you cannot vary the external circumstances much slower than the system itself because the system is arbitrarily slow. So many people believe that adiabatic theorem fails when G vanishes. But as you can see in this example of Born and Fock, it is possible for the gap to vanish at isolated points, and there is still an adiabatic theorem. It's slightly different adiabatic theorem, but there is still an adiabatic theorem. This theme of adiabatic theorem without a gap will be a recurring theme in the following. So now the next, I think an important somehow cornerstone of adiabatic evolution is this formula by Landau, Majorana, Zenner, Stückelberg from 1932. They considered the special case of 2 by 2 matrices, and the Hamiltonian is time dependent, T is time, and the rate of change is given by omega. And G is the smallest gap. If you plot the spectrum of this matrix, then you get 2 eigenvalues. It's a 2 by 2 matrix. And the 2 eigenvalues get closest at this point. And this gives you G. And one is interested in the situation, say, that at time minus infinity, you start at the lower branch, and you ask the question, what's the probability of tunneling to the upper branch? And this is an example, one of the very few examples in adiabatic evolutions which can be solved exactly and analytically, and not in terms of asymptotic or other series. And the result for infinitely long times is that the tunneling probability is exponentially small. It's e to the minus, and G over omega is the ratio of these 2 parameters. And the notion of adiabaticity is omega over G, okay? So the nice thing about this formula, it's exact. It gives an exponential tunneling. And as you can see, if you take the parameter omega over G, this formula is beyond perturbation theory because the perturbation expansion of e to the minus 1 over x for positive x has Taylor expansion, which is identically 0. So this is a result which goes beyond the perturbation theory. Yeah, yesterday when I had this dry run with Shadi, I don't know, I mentioned the fact that there was also Majorana's life were, ended with a tragic event. He disappeared on a boat that went from, I think, Napoli to Sicily. And then Shadi told me that Stuckelberg also didn't have a very happy old age. And he was apparently afflicted by, he became sick, mentally sick. So, but I tried to verify what Shadi told me by looking at Wikipedia. And Wikipedia is very, how do you say, very, is silent about these issues. But then I later found other amusing. Here is an amusing anecdote about Stuckelberg. He taught at Lausanne, and he used to bring his dog to classes. And the student would claim that the dog would know when Mr. Stuckelberg make a mistake, because he would start barking when Stuckelberg either made a mistake or got stuck on the board. And apparently the dog was just very sensitive to Stuckelberg, and he sensed when Stuckelberg was agitated or uneasy. Anyway, so there was a dog who, according to the students, understood physics. Now, the next result that I want to recall is a result of Kato from 1950. And what Kato succeeded in doing was, so adiabatic theorem graduated from an adiabatic theorem for matrices to adiabatic theorem for operators. If you look at Kato's paper, he wanted to find an extension of Born and Fock to the following cases, which were not covered by Born and Fock. So for example, suppose you have a ground state which is associated with a finite dimensional projection, but you're interested in the probability of tunneling into the continuum. So this is not covered by Born and Fock, because Born and Fock only studied matrices. And Toshio Kato wanted to generalize the adiabatic theorem to the case of operators. The other generalization we wanted to consider was the possibility that, say, the spectral projection on this eigenvalue is not one-dimensional, but higher dimensional. For example, in hydrogen, you have higher dimensional degeneracies. And this is, again, something which is not covered by Born and Fock. Now, it is true that this is a generalization, but I think Kato did much more than that, because he introduced a new technique and a geometric picture. And I would like to say something about this new technique and geometric picture, especially because this somehow connects nicely with Michael Berry, who is at the audience. So here is an idea, a geometric or mathematical idea that Kato introduced, which I like to call spectral evolution. And I think many other people also like to call it spectral evolution, but the name is not completely established. Kato didn't give it a name. And Matt Hastings liked to call it quasi-adiabaticity. So let me explain this notion. So I want to consider a spectral projection P, which is dependent on parameter, and I'll call the parameter S, okay? So here we have a spectral projection at some given S. Suppose this is 0, so this is the spectral projection at S equals 0. And the spectral projection changes continuously, or smoothly, in fact, and I get another spectral projection here, which is P of S. And we are interested in a unitary V, which is a function of S, which intertwines the two projections. So here is the formula. So I'm looking for a unitary V that would take P0 and map it precisely on PS. So this is an evolution that takes spectral subspaces to spectral subspaces because it takes projections to a projection. And what Kato asked, the question Kato asked is, how can you characterize the generator of this unitary evolution V? If you think in the language of adiabatic evolutions, one is looking for an evolution that satisfies an adiabatic theorem without an error. There is no error. It's a precise adiabatic evolution. Now, it is a computation. You take this formula. By definition, the generator of V is dk is IDV V dagger. And if you look at this formula, since V is unitary, then dk is Hermitian. And in order for this formula, for the intertwining formula to hold, dk has to satisfy a commutator equation. So the way to look at this commutator equation is that you are given P, the projection, which is a function of the parameter S. So you also know P and dP, and you want to find dk, which is unknown, which is a solution of the commutator equation. So this equation was written by Kato, and I'll discuss some solutions of this equation. Now, if you look at this equation, it is, I think, clear by inspection that the solution of dk is not unique, because I can add, for example, to dk anything that would commute with P, for example, any function of P, and it would still satisfy this equation. So the equation for the generator is not, does not define the generator uniquely. And as you will see, various people picked various different generators for different purposes. They were useful in various contexts. Now, I want to, before I describe the choice that Kato picked for this generator, I want to tell you something truly elementary, so which is largely disconnected from anything I told you until now. It's a very simple identity that I liked a lot, and I found it useful in many contexts. And the derivation of this formula is in 3 lines. I would like to describe it to you because I think it's an amusing, simple formula that I like. So if you take a projection, so by definition, a projection P square equal P. And if I differentiate it, then by Leibniz rule, I get on the left side 2 terms, PdP plus dPP. And on the right side, I get just 1 term, dP. Now, if you take this equation and hit it on the left, for example, by P, and use the fact that P square is P, you get this identity, that P dPP is always 0. And this is a nice formula that I found useful in many circumstances. It is analog to something that we learn in elementary vector analysis, that if you have a unit vector which is changing in time, so it's still a unit vector, then it necessarily moves on a ball, then the differential of this unit vector dn is always tangent to the ball. So this in some sense is the analog of this for matrices. Now why did I tell you this nice formula? So here is one way to use it. So we were interested in solving this commutator equation, that the commutator of dk with P is IdP, so that this would define for us a generator of adiabatic evolution. And Kato guessed the following solution: take dk, the commutator of dP with P. Now, if you use this identity, you substitute it in here, you immediately see that this gives this gives a generator of spectral evolution. Now, this IDPP, the commutator, is indeed Hermitian. And in some sense, this is the mother of adiabatic curvature, which was discovered by Michael Berry in the 80s. Of course, Michael had this wonderful insight that one should look at adiabatic evolutions over control space, which is higher dimensional, which is something Kato didn't consider. But anyway, Kato wrote this formula, which gives a formula for parallel transport. I may say something about this later. Okay, I mentioned before that decay is not unique. And here is something that Rudi Zeiler and I encountered. We wanted to extend the result of Kato to the following scenario. Suppose you're interested in the case that you start in the continuous spectrum, there is a gap, and there is a continuous spectrum on the top. So this was not discussed by Kato, because Kato assumed that P was a finite dimensional projection. But you would naturally think that if you start in this spectral subspace, then the gap gives you some protection and you don't infiltrate into this other part of the continuous spectrum. And the way we addressed this scenario was by picking another generator for spectral evolution. And this is the following generator. Take the Hamiltonian of the system plus I, the commutator P dot P. This is the generator picked by Kato, right? Which is, we know is a spectral generates spectral evolution because it satisfies the equation which we just checked. But you see that if you add to this generator picked by Kato H, since H commutes with P, then K dot is also a generator of spectral evolution. Now, the nice thing about this formula is that now you see the left-hand side, K dot, is a generator of spectral evolution, which means that it satisfies the adiabatic theorem without an error. But on the right-hand side, you see that this is made from the Hamiltonian plus a term, the term which was picked by Kato. But how does this term look like? It is made from P dot. So since it is made from P dot, if the circumstances change adiabatically, P dot is a small quantity. So this is proportional to the notion of adiabaticity. And therefore, you see from here a kind of a very simple way why there should be something like an adiabatic theorem, because the true evolution is close to a spectral evolution by a term which is proportional to the adiabaticity. And in fact, one can use this observation to prove an adiabatic theorem. Now, this thing was this formula, or this point of view, was discovered by Michael Berry in 2009, and he gave it a different twist, which is beautiful, which is like this, that you see, you can take the Hamiltonian and you can add to it something small, and then you kill all tunneling. There will be no tunneling whatsoever. If there is no tunneling whatsoever, then you don't have to drive the system slowly to be in the spectral subspace. You can move as fast as you want. And this then somehow generated, or this created a new area and a new field in physics where people are interested in making small controls of adiabatic evolutions, which allow you to drive the system as fast as you want. And this is known as shortcuts to adiabaticity. And so the Kato generator, for example, plays a role in this nice theory, but there are also other ways of getting this, of making these shortcuts to adiabaticity, but this is one that I like. which is due to Michael Berry and uses Cato's thing. Now I'd like to mention here is another adiabatic theorem, which looks a little crazy. This is an adiabatic theorem without a gap condition whatsoever. Now, the motivation for the adiabatic theorem comes from a very simple physical observation. Suppose you want to consider the hydrogen atom and you say in a weak magnetic field and you want to change the direction of the magnetic field. Then you would expect the adiabatic theorem to work. But suppose you take, instead of the standard picture of the hydrogen atom as described by Schrödinger equation, a more, how would you say, a more general framework where I also include the photons in the system. I want to consider the Hamiltonian associated with QED. Now, you would expect that the fact that there are soft red photons all around you, which would close the gap for the entire Hamiltonian, should not kill the adiabatic theorem, even though there is no gap. And so Alex Elgar at the time was my graduate student, and I told him that there should be such a theorem. And Alex found such a theorem, and in fact, when he found the theorem, we told the theorem to Michael Eisenman, who proposed a substantial simplification in the proof. And anyway, this is the theorem that gives an adiabatic theorem, and there is no gap condition whatsoever. There is one, how would I say, one unpleasant thing about this adiabatic theorem is that it gives an error which is little o of 1. So there is no, it doesn't give an effective error bound. And sometimes I like to think of this adiabatic theorem as a version of, as a non-commutative analog of something we know, that if you have a function which is integrable, then its Fourier transform decay at infinity is 0, but you can't say anything about the rate. So this is the last adiabatic theorem I wanted to mention. And I would, let's post, no, I'm sorry, there is a wonderful development that I still want to mention. And this is a recent development of the last 10 years or so, adiabatic theorem for many body systems. So Matt Hastings invented or rediscovered again this notion of spectral evolution, except that he called it quasi-adiabatic evolution. And he wanted to find, again, a generator of adiabatic evolution. But since he was interested in many body systems, he wanted the generator to be a local many-body operator. So what do I mean by a local? So if we take this very silly example of Heidegger A, that the particle can hop from, say, site K to site J, you don't want the K and J to be too far apart. So you want, by local, I mean that particles don't hop arbitrarily large distances. And since, for example, the Cato generator is made from projections, it does not necessarily have this good localization property. So it's not clear that it's a good local Hamiltonian. And basically what Matt Hastings found is another generator, which is written here. And this generator is made with a function W of t, which is plotted here. The function is rapidly decaying, and you look at dh is the variation of h with the parameter, with the adiabaticity, with the, say, time scale of the problem, and you decorate it with the generator of evolution e to the iht, e to the minus iht, and you integrate. Now, the beautiful thing about this formula is that since w of t is rapidly decaying, you really should think of this, that w of t is, the integral is on a finite interval, say from -1 to 1. And then you can expand e to the IHT and DH, and H and DH being physical Hamiltonians would be local, and their powers would also be local. So this formula creates a generator of spectral evolution, but for a decay which inherits the localization property of the physical Hamiltonian we want to study. Now, this by itself is not enough to prove adiabatic theorems, and you have to combine it with Lieb-Robinson propagation estimates. And this goes beyond things I understand or know, but I think it's a nice recent twist of this spectral evolution. Shall I make a stop and ask if people are protesting?
A quick comment.
Check that I have anybody left in the audience. Yes.
When you say inherits the localization of H, you probably meant locality of H.
Yes.
And you do not assume Anderson localization or anything like this, just local structure of H.
Precisely. Sorry about the misuse. Right. Mm-hmm. Okay.
But hi, Joseph. This is Ping Ao.
Hi, Ping.
Just one comment, since also Mike is here. Mike. We also kind of work anticipate the shortcuts to adiabaticity, and in 2000, I can send you the work. A little bit different twist than what Michael did.
Yes. Good. I'll be happy to learn about this.
Yossi,
Michael, do you want to read?
Yes, just a comment. Since you like history, concerning classical adiabatic theorem, I wonder if you know a most unusual paper by Dirac in 1925, just before he published his famous papers, which was this point. He was interested in old quantum theory and adiabatic theorem, but he realized that they apply in one dimension and give you exponentially good conservation. But he understood that if you go to more dimensions, you hit resonances, classical resonances, which are an obstruction. And he goes through an astonishing amount of number theory, very un-Diracish and a bit reminiscent of later papers by the Arnold group, in which he, if I remember correctly, and I'm just trying to find the paper now, he shows, well, you still have an adiabatic theory, but it's not exponentially good, it's square root good. Mm-hmm. Very remarkable paper.
I see. So is it related to these works later by Ed Ott about the...
Probably, but I'm thinking of the Russian group, Arnold, others, Nekhoroshev and others, much more sophisticated. But still, it's very unusual to see Dirac at this almost his first paper, not quite wrestling with number theory and resonances, numbers close to Diophantine theory, numbers close to rational and analyzing it's very unusual. And
so it's a precursor of KAM. Mm-hmm.
Well, that's right, and it's forgotten because quantum mechanics took over and nobody ever looked any more at classical adiabaticity till much later. Anyway, I just mentioned it.
Thank you. I think I learned it from you that nothing is discovered for the first time ever.
Yes, I applied to myself as well.
Yeah, this also was Mike told me.
So far as long. Anyway.
Okay, I'm moving backwards. Good. So I want to draw some pictures to entertain you. So it's easiest to draw pictures for two-level systems because pure quantum states of two-level systems live on the surface of a unit sphere. This is the Bloch sphere. And then one can plot orbits. So here is an orbit. Here is the Bloch sphere shown. And I plotted on this Bloch sphere the actual orbit in red performed by a particle which is influenced by a magnetic field which is moving along the blue line. So the instantaneous ground state would be represented by the blue line, whereas the physical evolution is decorated by these oscillations. And here is an exaggerated picture of the same thing. So here is the instantaneous state. Here is what the physical state does. It oscillates a lot. And I would like to discuss, in the following, I'd like to discuss a smooth version of the adiabatic theorem, which is represented by this yellow line. So what characterized the adiabatic limit, and this is part of the difficulty, is that the adiabatic limit is concerned with the case where the number of oscillations go to infinity, and they become wilder but tighter. So the way one approaches this instantaneous eigenstate is through wild oscillations. And this is one reason why the adiabatic theorem is subtle. In particular, if you look at the distance, I'll call this thing, right, the distance between the instantaneous state and the actual state, you can think of it as tunneling. This is how much you tunnel out of the spectral subspace. So the tunneling is a wild function as a function of parameter. In particular, you see that you are sometimes very, very close. The tunneling is minute, and then the tunneling is large and can be minute again. So the tunneling is not a one-way story. It's reversible. In Hamiltonian evolution, you can recap what you lose, which is not always what is happening in life. Okay, now let me make a small digression about the Fubini study speed, and because I want to discuss the fact that in adiabatic evolution we understand the role of a gap, but there is another object that we want to pay attention to, which is the Fubini study speed. I want to talk about this. This will also explain why the gap is a way, the gap dictates the internal time scale. Okay, so let's consider pure states. Pure states are described by density matrices whose square is itself. So pure states are described by projection. And the Fubini study distance or metric is d theta squared, is 1/2 d rho squared. So this is illustrated here. In the case, say in the simplest case of a Bloch sphere, we have ρ1, ρ2, and the angle between the two is 2 theta. Now the Fubini study speed, theta dot, would be 1/2 trace rho dot squared, just from this formula. And here's a simple, nice observation that if the evolution of rho is dictated by Heisenberg equation, the commutator of h of rho with dt, then the Fubini study speed is trace of h square rho minus trace h rho squared, which is just the energy uncertainty. So the Fubini study speed is just the energy uncertainty. In particular, you see now the relation that the gap dictates the internal time scale, because the gap tells you how much energy uncertainty you can get by distributing the state over different energies. And the other thing which is interesting in this formula, that if I consider instead of, if I consider a spectral projection which is depends on parameter p dot, then the rate of change of p dot gives me a measure of how the external circumstances of the system change. it's worthwhile to remark that the change in energy, E dot, is not an interesting quantity because it's a gauge-dependent quantity. So you would expect that the thing that should enter in adiabatic theorems are these two objects, P dot and the gap, because one says something about the external circumstances and the other one says something about the internal speeds. So, okay. Now, what makes the, one thing that makes the adiabatic limit interesting is that it is associated with a singular limit. So if I take the Schrödinger equation, the rate of change of psi equal h psi, and the tau is my time scale, the adiabatic limit is concerned with the case where tau is very, very large. I can change a unit of time from the ordinary time, which I call fast time, to S, which is called slow time. And then I can write this, the Schrödinger equation in this form, where in terms of slow time, tau hits the Hamiltonian. This notion of slow and fast time, by the way, were introduced already by Born and Fock in 1928. Now, the reason this is singular is that if you put tau on the left-hand side, then you see that the small parameter hits the leading derivative. So the adiabatic evolution is a study of a singular limit of a differential equation because the small parameter hits the leading derivative. Now, so this is one thing that makes the adiabatic theorem interesting. The other thing that makes the adiabatic limit interesting is that in terms of the time scale, you are interested in that real time. In the adiabatic limit, you allow the time to be huge because you're interested in the interval 0 to tau. Or in terms of slow time, you're interested in the interval, say, 0 to 1. In particular, in the adiabatic setting, you allow the change in the Hamiltonian to be of order 1. So this is what makes the adiabatic theorem, I think, interesting and also difficult. And the study of asymptotic limits, this is a joke I heard. There's a story, a description of asymptotica I learned from Michael Berry. I think that what is worse than biting an apple and discovering a worm in the apple is biting an apple and finding half a worm. And what is worse than finding half a worm is finding quarter of a worm. So finding no worm in the limit is actually the worst case. So well, thanks, Michael. I'm stealing from you lots of stuff. Okay, I think I can. Do I have to stop now? Have I already spoken too much?
Oh, you still got 10 minutes or so.
10 minutes. Okay, so let me. I don't know if I'll get to controlling the oscillations, but let me show a nice way of making an adiabatic expansion that I actually learned from Jean-Michel Graf, which only looks at the smooth part of adiabatic evolution. So let me describe this adiabatic expansion. It works like this. So we are interested in solving this equation, I psi dot tau h psi, where tau is a large parameter. And I want to expand psi in inverse powers of tau, but I'm only interested in the smooth part of the evolution. So if there are terms like if there are oscillatory terms like e to the minus I tau, I don't want to consider them because they have their expansion, their Taylor series is 0. So the way to make an adiabatic expansion is actually to split psi into two pieces. The first piece, which lives in the projection you are interested in, look at this picture. Here is, suppose I'm in this I mean the ground state, which is associated with the projection P. And then there is the rest of the spectrum, which is 1 minus P. Then I want to split psi into two pieces, alpha, which is the part which lives in P, and beta, which is the part that lives in the orthogonal complement. And now, if you assume that psi has this expansion, then there is a similar expansion for alpha and beta. And when you substitute it in the differential equation, you get a recursion relation. You get a recursion relation for beta, and you get a recursion relation for alpha. So the recursion relation for beta, the nth term in beta depends on the previous terms, n minus 1 of beta, and the previous terms in alpha. And the formula for alpha also, the formula for alpha is different. It only depends on beta at the same value of n and alpha at the same value of n. So the way to solve this equation is first to solve for beta, because it only depends on previous generations. And this formula is not a differential equation. This formula is an algebraic equation. If you know beta dot at alpha dot, then beta is just some linear operator that operates on this pair. On the other hand, for alpha, you get an ordinary differential equation, which depends on the beta, which you already found from this equation, and depends on the alpha. So there is an ODE. So the interesting thing is that the evolution in the spectral subspace P is in evolution governed by an ODE, while the evolution in the orthogonal complement is not governed by differential equation. It's an instantaneous evolution that is determined algebraically. So let me just give you the first two terms. So the nth zero term tells you that beta 0 is 0 because there are no negative n's, n can't be minus 1. So beta 0 is 0. And for the alpha 0, the leading term in the spectral subspace, you get the differential equation that the variation of alpha, if you project it into the spectral subspace, it's 0. This is the differential equation. It's a simple differential equation with the meaning that alpha is being parallel transported. You don't see motion in the spectral subspace. So here is an illustration what parallel transport is. Say, if I consider, say, the two-sphere, and I want to parallel transport a vector on a latitude, right? That's a latitude, right? If I want to parallel transport on a latitude, one way to do it is like this. You dress the sphere with the conical cap, which is tangent to the orbit you are interested in. Now, since a cone is a flat manifold, you know how to parallel transport a vector. If a vector starts here, pointing like that, then it is being parallel transport by keeping it the same direction, and it hits this point here. But since it's a cone, there is this conic angle here, which you have to close. So when you bring this angle down here, it points in a different direction, and this is the holonomy of this path. So this formula tells you that if you parallel transport along a closed path, you will in general not find yourself pointing in the same direction. This is precisely Berry's phase. So now let us now look at the part which lives outside of the kernel, outside the kernel in the orthogonal complement. So let me look at n equal 1. Then beta 1 is given by, I said it's not given by a differential equation. It's given by an algebraic equation, which is 1i over h p dot operated on alpha 0, which we know. And the tunneling probability to the first order in 1 over tau is the product of beta 1 with itself. And if you substitute this equation, you will get that alpha 0 is p dot 1 over h squared p dot alpha 0, it's necessarily a positive quantity. Now, there are several remarkable things about this formula. So the first thing that you notice that beta 1 at time 0 is not free for me to choose. It's not part of the initial data. You see, beta at time equals 0 will depend on alpha at time equals 0 and p dot. If p dot at time equals 0 is not 0, then beta 1 at time equals 0 will not be 0. And the other thing which is remarkable about this formula is that it's instantaneous, right? It depends only on circumstances at this given time. But it has no memory. So the tunneling to the order I computed here is memoryless. In particular, whenever p dot is 0, the tunneling vanishes, right? So in particular, for example, if at the end of the orbit p dot vanishes, then beta 1 at the end of the orbit vanishes. So this is why I drew this picture like this, that the tunneling, if there is no jerk, if the Hamiltonian changes with time, that it starts smoothly and then tapers off smoothly, then p dot would be 0 at the beginning and would be 0 at the end. And at least to this order in perturbation theory, you would not see tunneling. These ideas actually carry over to higher order in perturbation theory. Now, I also wanted to tell you about how one confronts the oscillations and how one shows that the oscillations are small, but I want to consult Joel and the...
I think you got a few minutes.
Hmm?
You got 2 minutes, 3 minutes.
You got 2 minutes, wow.
Okay, you can take, take 3.
Take 3, okay. Oh, you're just very kind. People are... Let me see. Actually, one thing in Zoom, which is very nice, I can find out how many people are left and how many people decided that they have better things to do. So I want to give an outline. How does one prove the adiabatic theorem even in the simplest setting? So I want to connect this with this notion of spectral evolution. So we want to solve, here is U is the physical evolution, which is governed by this the Schrödinger equation, with U at 0 equal 1. And we know about this spectral evolution V, which satisfies an adiabatic theorem without an error. And the one approach is to try and compare the spectral evolution with the true evolution. If the two are close, if omega is close to 1, then this is the content of the adiabatic theorem, that the evolution is close to being perfectly adiabatic. Now it's easy to compute omega minus 1 is given by the following oscillatory integral. Here you recognize this Kato P dot P, the commutator P dot P, and this is a Volterra type equation, and the integral is not a priori small because everything here is of order 1. Everything is of order 1, and the integration domain is also of order 1, so it's not a priori obvious that this is going to be small. The reason it is going to be small is that this term P dot P is highly oscillatory. So the integral is going to be small, not because the integrand is small, but because the integrand is highly oscillatory. And I use the notation that something with an index S is decorated by the spectral evolution. Now, I don't know, this is a historical remark. You know, for many years, people who looked at the adiabatic theorem were mostly interested in the question of how do you prove the adiabatic evolution, or under what circumstances is the adiabatic evolution better than any power even n, so it's exponentially good. But in recent years, especially since everybody got interested in quantum computing, the different perspective was given by these computer scientists. They basically just wanted to know when is omega minus 1 less than a third, but you want to guarantee that it's less than a third. So the focus changed a little bit, and therefore but for example, but they do care a lot. They are not happy to know that something is odd or something. They want to know numbers. So I'll try perhaps, oh, what happened? Okay, so I'd like to explain two basic tools that illustrate why the integral is small. So here is one observation, that if you look at the equation I u dot tau h u, this equation says that u is going to be rapidly oscillating. In particular, xs, which is made from uxu, by itself, if x is of order 1, then this is unitary. It is of order 1. But its derivative with respect to s is going to be large. And so here is write Hamilton's equation, which would say that the rate of xs, x dot, is given by the commutator with the Hamiltonian plus the way x changes, if x by itself is a time-dependent quantity. And if you look at this equation, then this object is of order 1, this object is of order tau, and so is this object. But the interesting thing that this thing will be now, the self-averaging of x with h will be small, of order 1 over tau. Why? Because this is a complete derivative. Since this is a complete derivative, when I integrate it, I get terms which are of order 1. And this by itself is of order 1. So when I divide through by tau, this is going to be small. So commutators with h tend to self-average and be small. So this is one idea. And the next idea that I want to explain is that you see in the equation omega minus 1 was not a commutator with h, but was a commutator with p. So you would see that one way to prove an adiabatic theorem would be if there was a way to replace the commutator with p with a commutator with h. And it turns out that you can, and this is where the gap condition enters. The formula, if you want to replace a commutator with p with a commutator with h, then you x would replace p by this formula. X is the integral over the resolvent p dot r. Now this formula, if p dot is of order 1, x would be also of order 1, provided you have a gap. The order of magnitude of x would be p dot divided by the gap, and r is the resolvent. So when you combine these two ideas, you get into the statement that omega minus 1 is of order 1 over tau. And the way the gap enters into this equation is because p dot is h dot divided by the gap, and this tilde, which appears here, x is defined by this tilde, and the tilde also involves a gap. So, so I'd like to conclude by thanking people who taught me everything I know about adiabatic theorem. They are my colleague Rudi Zeiler, John Michele Graf, Martin Frass, who taught me about the adiabatic theorem for many-body systems, and Alex Elgart. And thank you all for listening.
No, thank you very much, Yossi. Let's us unmute ourselves and give an applause for Yossi for a very, very, very nice talk. I think,
it's a real masterclass.
Yes. Let's do some questions.
Thank you.
Are there any questions or comments?
Yes, may I say something again?
Sure, Michael.
Sure.
Okay. Yossi, on this question of taming the oscillations, there's a way of doing it, which I found in connection with geometric phases long ago, but it's then much more general, which is you can make a series of unitary transformations clinging ever more closely to the Hamiltonian. It's like choosing ever more close to the Hamiltonian bases. And it turns out that this makes the oscillations smaller and smaller. But the series must diverge. And if it didn't diverge, then there would be no transition. In terms of phases, there would just be a convergent series and they wouldn't get the exponential. So you can put it in a dramatic way. Since transitions are the way in which we explain how things happen in the world, you can say, it's exaggerating a bit, if that series didn't diverge, nothing would ever happen in the world, okay? Now, you can get something more from this, because you can ask the question, you have this exponentially small transition, how does it happen as time passes? Well, usually this exponentially small change is lost in the oscillations, which are actually, although they're still small in slowness, they're power law small. But if you choose this divergence and you stop at the right place, then you find that the oscillations are exponentially small and the transition happens near a certain time. It's to do with universal properties of asymptotic series, certain which you can calculate, and you can see exactly how it happens. It switches on like an error function. So there's a lot of related work on divergent series, which followed, in my case, actually from this understanding of adiabaticity, but it's actually much more general. So it's another context. You can tame the oscillations, but never completely.
Mm-hmm. And how? What precisely does one mean by transitions?
The exponentially small transition to the other state, the non-adiabatic exponentially small transition to the state you didn't start in, the one you don't want.
Yeah.
Mm-hmm.
Thank you.
Thank you, Michael. Are there any other comments or questions? If not,
can I still ask a question?
Sure.
So I think most of all, the adiabatic theorem that was discussed was kind of for closed systems, Hamiltonian systems, but surely there are also things for open systems. And I was wondering, what is the state for even the effective equations which are nonlinear, like Gross-Pitaevsky equation or so? Are there also adiabatic theorems for that, corresponding to like an experimental situation where you are losing a trap or adding a potential in a very small way? Does that exist also?
So I don't know anything about the adiabatic equations for nonlinear systems. I think Avi Sofer probably does, but it is true for open systems. I do know about adiabatic theorems for, say, Lindblad type operators. They are still linear, and I can say something amusing about that. The most interesting thing about the adiabatic theorem for Lindblad type equations, which are non-self-adjoint, is that the tunneling stops being reversible. You know, in Hamiltonian evolution, you can make, you can always recover everything by, if you control the system right? If you, for example, stop the evolution sufficiently smoothly, then you can make the error arbitrarily small. But in open systems, if you lose something, you lose it forever. It doesn't come back. You can't get it. It's a little bit like friction. It goes one way, doesn't come back. So,
and do you see there a difference between Lindbladians, which are, say, satisfying detail balance, or ones which do not satisfy detail balance?
The result I mentioned is I think pretty general, but so at least the issue of detail balance didn't enter.
Okay.
At least for
and
this
for
result. This is a result
Gross-Pitaevsky,
again. But for Gross-Pitaevsky, I think Avi would be in a better position than me to say something about this.
May I add a comment here?
Yes.
Yeah, and for the open system, and we did a study, it's quite a while ago, on dissipative Lambda-Zender transition. So I think our result shows some kind of adiabaticity remain. Other parts get lost, as Joseph said. So that's our study. Is open system is within this Feynman-Verlan caldera-Lake formulation of the open system. So you might view it as more general than the Lindemann equation. Yeah, with
it's more general.
Yeah, more general Lindemann equation.
Are there any other comments or questions?
Yeah,
Thank you.
Let me comment on this. The open system case. I mean, one simple example is to look at the nonlinear Schrödinger equation, which preserves the energy and the L2 norm. But you will still see that the ground state, for example, you want to follow the ground state, you see that the norm of the ground state in the nonlinear case changes as you move. And therefore, this beautiful formula that uses unitarity and the fact that you have a nice projection and that you take the derivative of p squared and you write it as PdP, will not hold unless you do something else. And that's really the main issue, also will be for open systems.
Joel will allow me another comment.
Yes.
It might help. The simplest context in this present discussion is if you just have an ordinary non-Hermitian Hamiltonian as a model in different areas of physics. And Yossi, your colleague Nimrod Moiseev discovered numerically that this non-reversibility, was very surprised by it. So one of the states clings and the other one doesn't, makes transitions. But actually, this follows rather simply from standard ideas in asymptotics to do with crossing of Stokes lines of divergent series. So it all fits together nicely, and it all linked by the concept of competition of exponentials. Now, in the case of a Hermitian, you have just phase factors. You don't have growing or decaying exponentials. But in the case of non-Hermitian Hamiltonians, you've got these decaying and growing exponentials of different states, and this has to be incorporated. And when it is, that you explain completely the numerical results that Nimrod found.
I see. Okay.
And now there's a lot of work on adiabatic theory phases as well for non-Hermitian Hamiltonians.
Yeah, I must say that I'm slightly biased against general. I can see the structure in Lindblad theory because it insists on some structure which is preserving positivity. But studying just non-Hermitian Hamiltonians without this requirement that it is positivity preserving, then at least in quantum mechanics, I think it is less.
No, but there's a long tradition of complex refractive index in optics describing absorption, just things that you don't want to know about because you don't care where things have gone. And in nuclear physics, the cloudy crystal ball model. I mean, there's a long history. Of course, you're quite right. If you want to justify rigorously, including the environment and whatever, then the Lindblad business comes in. But as models, they've been used for, well, more than a century.
Thank you very much. Any other urgent questions?
Just a quick thing. Yossi, I put in the chat the thing about the Stuckelberg that I referred to.
Oh, thank you.
There's a paper that you can read about it if you want.
Thank you very much. Thank you, Yossi, for a beautiful talk. Let's thank him again.
Thank you. Thank you very much. And it was nice really to see all familiar faces, and people I love and who we walked along our career together. So it's nice to see you all. Thank you.
Nice to see you. All the very best to everybody.
Bye.
Bye-bye. See you next
time.
Bye. Bye. Thank you. Bye-bye.
Bye.
Bye-bye.
Bye-bye, Michael.
Bye, everyone.
Hi, thanks.
Hi, Simone.
Hey. Yossi, actually, it was a beautiful talk. Could you send me the slides?
With pleasure.
Yeah.